All right. The next one will be the electrical power system monitoring check. This will go through all of our power generation systems and run a checkout on them. So the first thing we're gonna do is check our cryogenic H2 pressure indication. Both should be 225 to 260. We've got a nice green band, so we already know that that's good. Surge tank on the O2 pressure. So take a look at this. Cryogenic tanks, oxygen. 2 is a single function gauge, but 1 is a double function gauge. It can be switched between the surge tank and tank 1. So here, oxygen pressure indicator, tank 1, surge tank. We're on surge tank. That should be between 865 and 935. Again, wouldn't you know, nice green band. Same with tank 1. We'll switch it over to tank 1. We can see the gauge move. Again, nice green band. Same thing, 865 to 935. No tricky business here. We'll record the cryogenic tanks quantity H2 and O2. Again, 1 and 2 corresponding to each tank. Record these 4 quantities, and then we'll go to the fuel cell power plant check. Fuel cell power plant check will make sure each of the inline heaters are on. Fuel cell reacts talkbacks are all gray. So that's pH high. pH is a measure of acidity. If it's high, it'll go barber pole. If it's standard, it'll go gray. You want it to be on gray. Fuel cell radiator temp low. Again, if it's low, it'll go barber pole. If it's normal, it'll go gray. So the false condition is actually the true condition for the text written on the pan. Basically, gray just means normal, barber pole means off normal in this case. Fuel cell radiators 1, 2, and 3. They're not bypassed, they're on flow, so gray, gray, and gray. We can see we actually can't set it because of some circuit breakers, and we'll cover those in a bit. Now we'll go over the fuel cell indication. So your fuel cell indicator knob between fuel cells 1, 2, and 3. Again, fuel cells do hydrolysis to create electricity. So if you put in a crap ton of electricity, and you can split water into hydrogen and oxygen gas, don't try this at home. You'll actually make most likely chlorine gas because of the chlorine that's added to the water. The chlorine will bind to the hydrogen, so you actually get some chlorine gas on one side and you get pure oxygen on the other, but you know it's very dangerous. So don't do it with anything but distilled water. If you're going to do that, you can actually run that experiment with a 9-volt battery. And what's cool is that the hydrogen and the oxygen actually are they have electronegativity, and in their electronegativity is polar. So one will be drawn to the cathode and the other will be drawn to the anode. It's really, really cool. Again, distilled water, not tap water, okay? You've got your flow indications. Right now we're monitoring fuel cell 1. The flow, notice the different scale, the different readouts, but pounds per hour. So we've got about 0.6 pounds per hour. So the nominal flow will be 0.03 to 0.15. We've got 0.06 and yeah, anywhere between the green band. Fuel cell O2 flow indication. Again, anywhere between the green band. That's 0.25 to 1.2 pounds per hour. We have the fuel cell skin temperature. Again, between the green band, that's 390 to 450. Notice the 10x multiplier. And the fuel cell condensate exchange temperature. Again, we've got a very nice green band between 150 and 175. Off nominal on any of these gauges is cause for the fuel cell lights corresponding to which cell to go off on the caution and warning. Monitoring 1, 2, and 3, we are good on all 3. I like to put it back to 2 since 2 has the most load. It's connected to both main bus A and main bus B. If you're on the Apollo 13 and above configuration, that will be the nominal fuel cell configuration, in which case either fuel cells 1 and 2 will be having the most load. Fuel cell 3 will have a little bit less. So 1 or 2. But we are on 7 through 12, so we'll kick that on. And we'll monitor fuel cell 2. Next up is the DC volt amperage check. We'll verify main bus ties BAT AC and BAT BC are off. We'll click through fuel cell 1. There's no voltage on this. Readout only amperage. So you're going to record the amperage for fuel cell 1, and then real quick, we'll just back it up a little bit. Forgot to talk about this part. Depending on what mission you're flying, you'll have barber poles and talkbacks on your fuel cell main bus ties. Just make sure that they match your written checklist. So here on main bus A, only the fuel cell 3 talkback is barber pole, and on fuel cell 1 main bus B talkback is barber pole. I don't know why it says 2. There's only one fuel cell 1 talkback. But yeah, that will be barber pole. Fuel cells 2 and 3 talkbacks will be gray. Again, 1 and 2 talkbacks on main A will be gray. We'll record the amperage on fuel cell 1. Record the amperage on fuel cell 2. Record the amperage on fuel cell 3. Then we'll select main bus A. That should be between 26.5 and 31 volts DC. Main bus B. Between 26.5 and 31 volts DC. So I would just like to add that the fuel cells only get an amps readout, whereas the main buses only get a volts readout. And then the rest of the stuff, battery charger, the 3 batteries, and the 2 pyro batteries, they get both volts and amps. So that is an important thing that I'm just editing in here after the fact. BAT bus A, again, 31.5, this time to 38 volts DC. BAT bus B should be around the same, 31.5 to 38 volts DC. Less than 3 amps on both of those. No, it's main bus A and B, excuse me. These don't get the amps readout. It's the BAT bus ones that get the amps readout. My bad. Battery charger should be nothing, because we're not using it. Battery C should be 31.5 to 38. Less than 3 amps. And then Pyro battery A should be 36.5 to 37.5. Pyro battery B, 36.5 to 37.5. Back to main A. And the last thing we'll check is our AC power plant. We have 3 phases, phase A, phase B, phase C, and 2 buses. So bus 1 and bus 2. Make sure each shows 113 to 117 volts AC. AC stands for alternating current. It's a sinusoidal. DC stands for direct current. It's flat line. Okay, a couple of other things that we'll need to talk about for this one here. You can see I tried flipping the react switches. I've tried flipping the radiator switches. As part of the procedures for those, circuit breakers are open so that you don't bump them and accidentally mess something up. So to close a radiator or a react valve, circuit breakers corresponding to those have to be closed first. They're located down here on panel 226. You can see fuel cell 1, radiator, fuel cell 2, radiator, fuel cell 3, radiator, and that will allow us to do the control of the radiators, bypass and normal. Same thing applies for the fuel cell react valves, but I'm not going to do that because that'll kill our power. The other thing that came up is the main bus ties. I would like to point out that when you flip, for example, bat AC tie to on, only battery A is getting tied right now, and the reason only battery A is getting tied is because the battery C circuit breaker here on panel 275 with main bus A is open. We close that, we power up battery C. And this one going from B, C, if we close battery C, we send that over to the bat BC tie. You can see only batteries A go to main A, B goes to main B, and battery C can be cross-tied to both. We can see, same thing with the flight and post-landing bus. Bat A, bat B, bat C is another thing that needs to be closed. Down here on panel 250, we've got some similar stuff, except we can tie battery C to battery bus A. And when we do that, I'll show you when we tie this, we get the light brightness goes up a little. When we do that, we effectively, you can see light brightness goes up. We effectively make battery C and A as a common circuit now. So instead of going through the battery C tap and making it very much basically its bus, its own bus, we tie battery C into battery A, and battery A and C become the bat bus A. And the same thing is applied when we do battery C to bat bus B. So again, as demonstration, if I flick that, main bus B is tied to, or excuse me, bat B is tied to main bus B. And again, I can make battery C and battery B common to bat bus B. And that'll tie those up. So different ways that you can tie things. It's a very, you can tie it either by going like that and putting battery bus C, battery is technically its own bus, on both, you know, main A separately, or you can have them run together. So that's sort of the breakdown of what was occurring there earlier and why I said we would talk about this at a later point. That's sort of the electrical power plant situation, and I'll explain the battery charger separately.